Right then, so because this is an AS paper, there's a small section of multiple choice questions at the end of it. When you do your actual A-levels, you don't see any of these until paper 3, and there's a big wodge of them, 30 in a row, at the end of that final paper. I've used the word underestimated quite a lot in this walkthrough, and this is another place where I don't think that they're underestimated, but sometimes perhaps not given their due. Actually, this section is going to be difficult, right? Because often there are very plausible incorrect answers, things that you could very easily come up with in your calculator, for example, that are not correct. So let's kind of crack on. Some of them, though, will take way more than a minute, and some of them will take less than a minute, and that's the idea, is hopefully you get a bit of time back with the ones that are giveaways, but they're not necessarily going to be that many of them. One thing I will point out actually before we start is just technique wise, again, if you get to the point where your invigilator or whoever has said you've got 5 minutes left and you've left any of these blank, just put something, B, C. I'd go for C, right? There's no particular statistical reason for that, but just put something, for heaven's sake, because otherwise you're throwing away a 25% chance of just getting the answer right by accident. Okay, so do not leave any of them blank under any circumstances. The AQA's guidance here is pretty clear about how to fill them out. Something that's a bit mean is that they say you can't use additional sheets for working. That's just tight basically, because there's not always that much room, but whatever, we'll figure it out. So, question 10, definitely easing us in gently here. Which element is in the D block of the periodic table? Okay, I reckon my 3-year-old could do this because she can recognise simple letters, alright? But, just to be clear, we're looking for something that's got the symbol and the name that's in the D block. So we've got 4 answers: selenium, antimony, tantalum and lead. So again, this is just a bit of a time waster if you don't know where you're looking. So there's selenium, that's P block. Okay, what was the next one? Antimony, alright. Symbol for that is SB. Not necessarily going to know that, but you'd find it if you looked long enough. So that's a P block element as well. Tantalum, let's look for the symbol TA. There it is. And boom, answer, right? We're not going to even look at lead. What's the point? We know that tantalum's in the D block. That can be the only correct answer. That'd be a waste of time to look at lead. Which species contains an element with an oxidation state of +4? So there's not really quite enough room here, okay? Alright. Under here, oxygen's going to have an oxidation state of -2. To get from -4 to +1, nitrogen there must be +3, so it's not that one. Okay, so that's wrong. The chlorate ion, we actually mentioned this earlier in the walkthrough, but let's just pretend for a second like it's completely unseen. -6, we have to go up by +5 to get to -1, so it's not that one either. Okay, H2SO3, -2, -2, -2, +1, +1. If you're wondering how you know all this, like I've said before, you have to just learn some stuff, including very common oxidation states. So this time, we do have an element in the middle that's +4 because we've got +2 from your hydrogens and -6 from the oxygens. So that's -4. To get it to 0, which it is because it doesn't have a charge, the sulfur must be +4. So there we go. Don't need to check the phosphorus one because we know that that's the answer. Again, you're trying to save time. If you really want to and you don't feel confident with this answer, you can, but I'm not going to because I'm trying to model good practice, right? Right, then we're on to a calculation. Okay, so we've got 392 moles of gold. Okay, symbol for gold, let's pretend for a second that I don't know it. You might have to search for a little while to find it. Okay, I'm pretending to search. Searching. Oh, bloody hell, where is it? Oh, okay, here it is, right, down the bottom. Alright, AU. So that's relevant. We need to go back and just check. Relative atomic mass of 197. Why do we care about that? Well, if we've got this many moles and we've got the relative atomic mass, then we can calculate the mass of gold before we even do anything else. Notice how I've not even looked at the rest of the question yet. I basically got there and stopped, right? So we want to know mass. It's moles times mR, so 392 times 197. That's going to be quite a big number, isn't it? I guess 392 moles is quite a lot. Equals 77,224. Now, unit-wise, we mentioned this in an earlier question as well, grams. Anytime you do a mole calc, it's going to default to grams. That might need to be changed in a minute, having read ahead. We've then got this, which was going to be used to calculate a volume, right? Because it's talking about a three-dimensional object, a bar of gold, okay? And then it asks for the density of gold in kilograms per dm cubed. So the first thing we can do to help ourselves is that number that I just calculated. Let's divide it by 1,000, right? This one here. Divided by 1,000 equals 77.224 kilograms. So now we've got our mass, okay? And to calculate our density, we need a volume, and so that's going to involve us using the next part. So for the volume, we're just going to multiply these numbers together. So 10 by 10 by 40, 4,000 centimetres cubed, because the units given are all in centimetres. So as a volume, it's going to be centimetres cubed. Once again, we're going to need to do a conversion here, because actually we need it in dm cubed. So this is a bit like when you do a titration calc and that kind of thing. It needs to be divided by 1,000. So it's 4. Okay, 77.224 divided by 4 equals 19.306. That should match an answer. Yes, it does. It matches B. Okay, again, something that they do often here is round stuff. If you were out with your conversion, you could quite easily arrive at any of these other answers, right? If you didn't know exactly how to convert grams to kilograms, or decimeters cubed, or centimeters cubed to decimeters cubed, all right? If you're not sure about that, again, there's a bit of GCSE physics and maths involved here. Just density equals mass divided by volume. That's what I did in this step, in case that causes you any bother. Ions of two isotopes of iron are these two. So before we even look at the statements, I'm just going to point out that this one's lighter and this one's heavier, just because that might be relevant. The ions of both the isotopes have the electron configuration blah 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 blah. So straight away, if we look at the electron configuration, there's something that should be a red flag, which is ion is a d block element, and in d block elements the first electrons to go are always the 4s electrons. So any 4s electrons there, right, that means this is wrong, okay? And we're not going to bother saying what the correct electron configuration is because we don't need to, but we know that that's wrong. The ions of both the isotopes contain 26 neutrons. Let's think about that statement for a second, right? If iron is the same element, right, and it's got isotopes, the definition of isotopes are atoms of the same element with the same number of protons, right, that's a key part of the definition, and a different number of neutrons. So, gone, no. For the same reason, C doesn't make any sense, because if they're both iron, they must have exactly the same number of protons, because that's what makes iron iron, right? So that can't be right either. That does mean that we've arrived at the correct answer, okay, just by default, because it's the last one in the list and it's the only one that's not wrong so far. But we might as well look at it. After acceleration to the same kinetic energy, 56 Fe2 plus will move more slowly than 53 Fe2 plus. So actually that bit I did at the beginning is now relevant. So the heavier ion moves more slowly than the lighter ion. That's a fact you're supposed to know about your time of flight mass spectrometer, right? The idea that the ions enter at the same time, or the isotopes, sorry, enter at the same time they're given the same kinetic energy, but the lighter ones will reach the detector more quickly than the heavier ones. That's a fact you're supposed to know, to do with the relationship between kinetic energy, mass and velocity. So that's correct, right? Either by deduction that the rest of them are wrong, or by actually kind of knowing. Bit mean that one, because it's one of the ones where D is the correct answer. And anytime that's the case, it means you've got a little bit more work to do, because you have to rule out A, B and C, unless for whatever reason you go in reverse. Entirely up to you. Lovely. The successive ionisation energies for element X, which obviously is not an element, right? It's just a placeholder for something that we're about to identify, are shown in figure 3. So, if we look at this, what we have is a lowish number, a jump to an increase to a still fairly low number, a similar sort of increase, and then a red flag again. This big jump here is a change in energy level, not just a change in sub-level, but a change in energy level. To remind you of GCSE kind of modelling here, the idea is that those first 3 electrons are being taken from the outermost shell, and then the remaining 5 here that are provided in the data, they must be getting taken from an inner shell, right? That must be how it is. Okay? If you're wondering why, well, again, go back and look at your notes or watch a video about how ionisation energy works, but the simple answer is these ones are further away, okay? And they're, more easy, or the technical term is they require less ionisation energy to remove because they are further from the attractive force of the nucleus, right? So that big jump is definitely a change in energy level. What we're trying to arrive at here is the idea that it must be a group 3 element. So let's have a look at our candidates. Nitrogen, that's group 5. So no. Phosphorus, that's group 5 as well. Nope. Aluminium, that's group 3. But if we look carefully, there's also boron, which is also group 3. So this is a bit mean, because you really have to consider both of these things. It's got to be one of these two, because they're both group 3 elements. The clue lies in the rest of the data. So it could be either of them if you just look at this section, right? But if you include the wider proportion of the data and then go back and think about boron, there's something more fundamental about that, which is boron only actually has 5 electrons in the first place, whereas aluminium has 13. So if boron only has 5 electrons in the first place, the data would stop here, right? You couldn't remove more than 5 because you'd only have 5 ionisations, which means that this is incorrect and aluminium is the correct answer. That's mean, because if you're, doing this in a kind of dead straightforward and standard way, you'd probably see aluminium, see that that's group 3, and then just put that as the answer. Admittedly, you'd get it right, but if they put them in reverse order and you had boron first, then aluminium, then you could get punished for that, right? And to be fair, you should consider all the options, I guess, but most of the time, the simplest thing to do is to find the right answer and then just stop to save yourself time, because like I keep saying, these can be a real time sink, these questions. This is a sort of dead standard trend question. Which of these decreases down group 2? Well, let's look at A. Does first ionisation energy decrease down group 2? Yes, is the answer. Again, you have to kind of learn this, but the first IE graphs down any group look a bit like that. And it's for the same reason that we mentioned earlier, which is that as you go down a group, the sizes of atoms, their radii, increase, which puts the outer electron further from the nucleus. And the further it is from the nucleus, the less energy required to remove. So this is the correct answer. I'm not going to go through the others, but if you want to, you can have a quick look and rule them out. It's definitely A. Okay? So this is relevant for 2 questions. Refer to the unbalanced equation below when answering questions 16 and 17. In the balanced equation, the mole ratio for sulfuric acid to water is, Okay, so what they're basically saying is, can you balance this equation and can you use it to answer the questions? So there are a number of different ways you can do this, right? One is through rewriting it and trying to do it by trial and error, which will work eventually, but is it worth your time? Probably not. If I'm doing this exam paper, I probably put a star next to this and I leave it till last, and it might be one of the ones where the invigilator walks around and says, you have 5 minutes, and then I go, alright, forget it, B, whatever, right, A, C, D, doesn't matter. Having said that, I might as well talk through it because it is solvable, it's not impossible. It's just that there's probably quite a lot going on here. Okay, so probably the easiest way to do this is to consider the fact that there are no coefficients in front of the sulfur containing compounds on the right hand side of the arrow. If you're wondering why my attention's been drawn to them, first things first, I'm probably going to try and figure out how many moles of sulfuric I've got. So that means I'm looking wherever there's sulfur in the equation. There's only one compound that contains it on the left, which is the one that we need to balance, and there are two that contain it on the right. Why am I bothered about the fact there's no coefficient? Well, the AQA, although they can be very mean, they've been quite nice here because there's no gap in front of it. Basically what it means is that the two things that I've just highlighted, the chromium sulfate and the potassium sulfate, are balanced. So we can use that to our advantage, right? If we're literally just looking at the sulfur, right, 3 moles of S there, hopefully you understand why, because there's a subscript 3 for the sulfate ion, 1 mole of S there, okay, which means that number needs to be 4, because 3 plus 1 equals 4, and there's nothing else on the left hand side that contains sulfuric. Straight away then, A and B are wrong, because it's the mole ratio for sulfuric acid to water, so it must be 4 to something. Then the next bit, well, I think you just have to do this conventionally, don't you, right? We've got 8 hydrogens in this compound, 6 hydrogens in that compound. There's no other hydrogen on the left hand side, so that's 14 hydrogens, right? 0 hydrogens, 0 hydrogens, 0 hydrogens. So the only thing to do is to turn water into 14 hydrogens, which makes it 7 moles. Answer is C, right? That might look really hard, but actually, if you're systematic about it, and this is what these videos are intending to do, is to help you kind of grow this skill set a little bit, it's not actually that bad. It looks worse than it is, definitely. So I'm just going to get rid of these bits, but I'll leave the coefficients in case they're relevant for the next bit. Alright, so this is a redox question. What is the reducing agent in this reaction? So actually it's nothing to do with the ratios and everything to do with the redox changes. Best thing we can do here is probably zoom in a little bit, okay, because I'm going to label everything underneath the elements. Potassium's +1, it's always +1, right, unless it's potassium metal, which it's not in any form, unless it's pure potassium, it's going to be +1. You've got seven oxygens in this compound, that's -14. There are 2 potassiums, +2, so chromium must start out at +6, okay, because that's going to give you +12. I feel like I need to just do that whilst we're so zoomed in. So the chromium starts at +6, potassium +1, oxygen -2, okay. You've then got this compound, which is a strange diprotic acid. This thing comes up a lot actually in year 13 chemistry, so you might not know much about it yet if you're just just starting out year 13, or if you're still in year 12. So hydrogen +1, there's 2 of them actually, so I should write it twice, okay. Oxygen -2, so that's -8. So that means the carbon in this must be +3. You don't normally have to look at the oxidation state of carbon, but that's what it must be, right? So just to summarise, +1, +3, -2. Sulfuric acid, +1, +1, -2, -2, -2, -2, -8, +2. Sulfur must be +6. There's only one of them. Okay. Whew. Let's keep going. The chromium sulfate, right, is a weird one. The easiest way to do this actually is to remember that the charge on the sulfate ion is -2, right? For figuring out the chromium. Okay, so if there's 3 of those, then that's basically 6 minus from the sulfate ions in total, which means that the chromium must be +3. So straight away not straight away, hardly straight away at all, but now we have a change. If you were kind of looking carefully back at stuff, the chromium has undergone reduction. What did it ask us about? What's the reducing agent? So we're looking for the thing that's been oxidized. Okay, so that's not our answer basically. Is it one of the options? Yeah, okay, so it's not that, and that's why it's there to fool you. Just to be clear, the chromium has undergone reduction, therefore it must have been an oxidizing agent, so we're looking for the thing that's undergone oxidation. We can check sulfur in each sulfate ion. In fact, it's probably easier to do that up here, because that's not going to be any different. -2, -2, -2, -2, right? To get to -2 from -8 +6. So that's still the same. Sulfur hasn't undergone oxidation. And actually it won't do, because +6 is the highest oxidation state of sulfur. +1, +1, -2, right? That's the same. Yeah, oxygen's always -2 on the left. Hydrogen started out as +1, so that hasn't changed either. So we haven't got many choices left now. Carbon dioxide, -2, -2, -4, +4, okay. +4, +3. That's an increase in oxidation state. Carbon is the thing that's been oxidized, or carbon in the ethane dioate ion, which is this thing. Flipping heck. That is a tough question for a year 12 paper. That's really, really not very fair, just from the point of view of somebody who teaches the ethane dioate stuff all in year 13. Like, you barely even encounter that ion and that acid that this ion comes from. You barely even encounter it in year 12. So, you know, if you had to go at this question previously and you couldn't get it right, don't feel bad. Let's keep going. From the sort of ridiculous to the sublime, which substance exists as a macromolecule? Metallic? Yes. That was quick. If you don't remember that silicon dioxide's macromolecular, you need to, because you get questions like this, right? That's enough of that. So we've got an equilibrium question, okay? I use this sometimes actually with GCSE groups, just as a sort of challenge question for anyone that's doing pretty well with GCSE equilibrium. It's all quite logical. It's just, to be honest, it's just hard to read, right? It just takes time to read. So there's all this stuff. I'm not going to read it all out, but crucial bits. When the syringe is placed in the hot oven, okay, so increasing the temperature, the mixture becomes darker in colour, okay? So let's just clarify all the things we know. Increase in temperature favours the endothermic direction by Le Chatelier's principle. So that still doesn't tell us whether endothermic is forwards or backwards yet, but there's a bit more to it than that, okay? But we know that, okay? So the endothermic direction must produce the darker coloured gas, because one of them's paler and one of them's darker, okay? I missed this bit because I went straight for the temperature, but when the plunger is pushed further into the syringe, the pressure increases and the mixture becomes paler in colour. So again, before we even think about the colour, increase in pressure favours the direction with fewer moles. Again, this is by Le Chatelier's principle. You just have to learn this set of rules, otherwise you've got no chance for this type of question. So increasing the pressure favours the direction with fewer moles. So we do now know something. an increase in pressure must have favoured the direction with fewer moles, which is this side, meaning when this happens, this bit, it's going forwards, okay? Which means that N2O4 must be the paler compound and NO2 must be the darker compound. If you don't quite follow that, then you can always rewind the video. I probably didn't explain this bit quite as well as I should have done. What we're basically doing is using this logic puzzle to figure out that if you increase pressure, it favours the direction with fewer moles. The direction with fewer moles is this way because the coefficients tell us so, 2 moles of NO2, 1 mole of N2O4. Increasing the pressure makes the mixture go paler. That means that the N2O4 must be the pale gas and the NO2 must be the darker brown gas. So then, let's go back to the previous section about endothermic and exothermic. Increasing the temperature favours the endothermic direction, and what actually happened here was, if we increase the temperature, the mixture became darker, so it must be endo in that direction. That means that by logic, it's exo in that direction. So, what we deduced was NO2 is brown, NO2 is brown, NO2 is colourless, NO2 is colourless. Those two are useless because we know that the nitrogen dioxide is brown now. We figured that out. Then the forward reaction is exothermic, tick, there we go. Because the forward reaction is not endothermic, it's the reverse reaction that's endothermic. That was another thing that we figured out, so B is also incorrect. Okay, which molecule has the largest dipole? Let's draw him. So this I'm not going to arrive at using the method that we did earlier, but if you do, you've got 2 lone pairs to do with the fact that chlorine's in group 7 basically, right? BF3 just looks like that, so that's got no lone pairs and it's completely symmetrical. SF6, this is your classic example of an octahedral molecule, also has no lone pairs and is completely symmetrical. Okay, CF4, this will have dead polar bonds because the carbon-fluorine bond is dead polar, but it's also completely symmetrical because it's a tetrahedral molecule. I realise and appreciate that I went through those very quickly, right? But you'd have to kind of work out the shape and positioning of lone pairs and what have you. So the only thing really that's got possibly polar bonds and a big region of electron density is this thing, which means that the answer is A. Everything else is going to have possibly polar bonds, but whenever you've got that element of symmetry, the dipoles cancel, so all 3 of these things are going to have no net dipole, no overall molecular dipole moment, so it has to be ClF3. This should be on paper 2, surely. In a molecule of a hydrocarbon, the fraction of biomass of carbon is 9/11. What is the empirical formula of the hydrocarbon? Okay, so hold on. 9/11, right? So that's 81%. Just to sort of, well, it's 81, it's a weird recurring number, but roughly 81%. So then what is the empirical formula of the hydrocarbon? Well, for this one, 12 plus 1 equals 13. 12 over 13 times 100 equals, so what I'm trying to do is I'm trying to work out the percentage biomass of carbon in each of these. That's like 92%, so no good. 12 plus 3 equals 15. 12 over 15 times 100 equals, that one's bob on 80, so that's no good either. Okay, so it's not that. 12 times 3 plus 8, so that's 44, right? 12, well no, sorry, it'd be 36 over 44. 36 over 44, because it's 3 times 12 if you're wondering, times 100. That's 9/11, yeah, 81%, there we go. It's that one. So we won't bother with that. Whew. Nearly done now. There's only a few more left. 30 centimetres cubed of xenon, is mixed with 20 centimetres cubed of fluorine. This is how they react. Assume that the temperature and pressure remain constant. What is the volume of final volume of gas after the reaction is complete? So this, I've had this question brought to me lots and lots of times because it's tricky, right? So first of all, this here is going to be a distractor, presumably. It's not going to be as simple as 30 plus 20. There's going to be a bit more to it than that. The next thing is, let's get what we can from the equation, which is the molar ratio is 1 to 1, and the number of moles of the product is also 1. The reason that matters is, if you're assuming that the temperature and pressure of gases remain constant, then you can basically treat the volumes as you would treat numbers of moles. So let's just thrash this bit out in a slightly larger kind of equation. If there's 30 centimetres cubed of that, and there's 20 centimetres cubed of that, but they react in a ratio 1 to 1, then one of the reactants is in excess. And if you think about it carefully, it's really obvious which it is. It's the xenon, right? So that's in excess. That's the limiting reagent. Because this is the limiting reagent, this number can then basically be translated to the product side, right? Which means you get 20 centimetres cubed of xenon difluoride, okay? But that's still not the answer. That's another distractor. Because as the reaction proceeds, there'll be 0 of this left, but because this was in excess, there'll be 10 of it left, and there'll be 20 of this formed, right? 10 plus 20 is 30, so our answer is C, because it's the total volume of gas, final volume of gas, after the reaction's complete. That's quite tricky, but again, once you've done one of these, the rest of them do get slightly easier. Which of the following solutions would blah, 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 blah. So we just need to calculate numbers of moles of each of these things and then take care with the formulae as well. All right, so 50 over 1,000 times 1, 0.05 moles. Well, that looks like the correct answer to me, but let's just double check that I've not done something stupid. 100 over 1,000 times 2, so that's 0.2, so that doesn't look like a sensible answer. Let's just check the barium hydroxide answers. 100 over 1,000 times 2, that's the same as the previous one, isn't it? 0.2 moles, okay. And then 50 over 1,000, I was being stupid, I've just realised why, we'll sort it out in a minute, times 1. 0.05 moles. Okay, so I said that this might be the correct answer. I'm totally wrong, so let's talk about why. Sulfuric acid is diprotic. It has 2 hydrogen ions in it, so it would react with 2 moles of potassium hydroxide, right? Which basically means that if you had 0.05 moles of that, you'd only need 0.025 moles of that, which is what makes it the wrong answer, okay? We also can't have 0.2 moles of that because that would give you exactly 0.1 moles of that needed. So basically, potassium hydroxide's out. Then, reaction between barium hydroxide and sulfuric, it balances out 1 to 1 basically. If you want to try and write it out as an acid-base reaction, you can. I'm not going to, but it does balance out. So if we've got 0.2 of that, you'd have 0.2 of that, which is no good. But if you have 0.05 of that, then you have 0.05 of that, which is exactly what the answer wants. So it's D. Okay. Again, this is kind of tough for year 12 stuff because you haven't done loads about diprotic acids or dibasic alkalis like barium hydroxide. Okay. Let's go out on a high then. This is another one, just like that xenon difluoride question that I've had quite a few times, alright, so I'm fairly familiar with this question actually now, although there's always a chance that I forget stuff, okay? So, you've got to read all this stuff. There's two equations to take into account. We start with 2 actual moles of that, as well as a ratio of 2, right? That's sodium azide. As well as a ratio of 2, there's actually 2 moles of it. So 2 moles of sodium will be made and 3 moles of nitrogen gas will be formed. Okay? So that's from one reaction. You're then told that the sodium metal then reacts with potassium nitrate to produce more nitrogen gas. Okay? So there isn't just 3 moles of N2. That's part of it. There must be some more N2 from this reaction. And that's the bit that's sometimes hard to point for people to pick up on. We said that we had 2 moles of sodium. So I'm going to write 2 over there because that's the actual number of moles we've got. The ratio is 10 to whatever, but there's actually 2 moles. So the ratio between the relevant compounds is 10 to 1, which means that we must get an actual 0.2 moles of nitrogen. The sum of those two numbers is 3.2, because those are the only sources of nitrogen. Then we need to know how many molecules of N2 will be formed, so we need to use the Avogadro constant. I mentioned this earlier. If it's there, you need to use it. 3.2 times L, which is the Avogadro constant, is going to give us one of these numbers. 1.927 times 10 to the 24. Oh, there it is, 1.93. So it's B. Okay, that's your answer. So I hope you found this useful. I'm a bit conscious of the fact that I maybe went a bit fast at certain points, but it's quite a long process going through an entire exam paper. So I don't want each individual question to take forever. If you do want further sort of guidance about anything in particular, then do get in touch. Feel free to email me, and I'll do my best to try and explain certain ones in a little bit more depth. I think it's the multiple choice questions that probably got a bit of a rushed explanation, but like I said, it's a fairly big section. I've spent over half an hour, nearly 40 minutes doing just this bit because I'm commenting on everything. But like I say, I hope that it's been useful. All right.